Now, all these next problems rely on us to do partial fractions to solve our integration problem. So when we get the 1 over x minus 1 x minus 2, we know we can't integrate that. There's no way we can just integrate that as it is. We need to manipulate it. So we're going to use the partial fractions. So you can see how the partial fraction workings in blue to get down to our functions here. So check through that. We've gone through videos on partial fractions, so you should be getting pretty good at doing partial fractions. So have a look at the working there, and it comes down to the minus 1 on x minus 1 and 1 on x minus 2. Now the good thing about that is that these work out just to be nice log functions. So we can write it like that. We can leave it at that point. That's why I put a little tick there, because we can leave it at that point. A lot of times in text you'll see it written in these forms where it's the minus natural log, so and plus, so we can write that as one log function with a division. So just be wary when you're seeing that. That's what it means. But partial fractions first to solve the problem. Help solve the problem. And again here, all the blue in these ones are where I've solved the partial fractions first. So we've done x plus 2. We want to integrate that. We need to get back to two separate terms, two separate fractions to do that. And again, once we've got that through the partial fractions, we're able to find that very easily. Again, we could leave the in terms of our log functions there once we've integrated. Although you could write, you'll see it written like this in text, where because it's positive 4 natural log of x, well the 4 can go up as a power, and because it was positive it would be up there, and the negative is going to be dividing, and the 3 goes up to be the power there of x minus 1, using our log laws that we know out. So this time the x squared plus 2 on x minus 1, same degree, so we have to do a division, or I've just done a looked at it and gone, well, x minus 1 x minus 2 will expand out to give us x squared minus 3x plus 2. Well, to decompose it this way, I can put in a minus 3 and put a plus 3x in there. So that comes down to 1. So that's nice, because they both cancel out, gives me 1. There's where our partial fraction is going to come in. So the 3x on the x minus 1, x minus 2 can be broken down in partial fractions, because again we're back to the stage where 1 degree less than the 2 there, and it's a multiplication of linear factors, so we know it can come down to fractions there. And then we get the 1 minus the 3 on x minus 1 plus the 6 on x minus 2. Integrate 1 gives us x, integrate 3 on x minus 1 gives us the minus 3 natural log of x minus 1, and 6 on the x minus 2, 6 natural log of x minus 2 when we integrate. Again, we can put our 6 in the power there. Because it's minus 3, we'll put the 3 and divide there by using our log laws. This one pretty straightforward, because it's 1 degree less than that one, and we can get this down to linear factors. If we can't get down to nice linear factors, well, that's another type of problem we have to face. But when we see this and we can get down to nice linear factors, we're going with partial fractions. So that's where we've got to look for and be discerning about where we're going to bring in partial fractions to get our expression, and then do our integration. Because once we've got to that expression, the integration is not too hard. It's really just 2-unit work from that. Like 2-unit students would be expected to be able to integrate that function. Maybe not take it to there, but they should be able to integrate those functions down to log functions. So the integration is not the hard part. It's the manipulation beforehand. X cubed plus 5 and x squared plus x. Well, I've done a polynomial division of this one. I haven't done shown you the full polynomial division, but it would come down to x minus 1 times the x squared plus x, and our remainder would be x squared plus x plus 5. So when we do the division, that would be our division transformation, which I can start playing with there, and that's going to divide and give us just x minus 1, because it goes in x minus 1 times with x plus 5 remainder. And again, well, that's 1 degree less than the x squared plus x, so we can start to get a situation, because we factorize into distinct linear expressions, and so partial fractions are in the case. So we can solve, and we get a is equal to 5, b is equal to minus 4. So there's our partial fractions. Integrate x gives us x squared on 2, integrate 1 gives us x, 5 on x integrates to 5 natural log of x, and 4 on x plus 1 gives us 4 natural log of x plus 1. So you can see the process stays the same. It's just harder sometimes when you look at distinct factors. But remember, it's a quadratic that's irreducible, so we have to solve for bx plus c. So the process of coming into polynomial to the partial fractions allows us to get it our numerator and denominator and be able to split them up there and be able to get the 3 expressions. Now, just be wary. We've got 2 on x plus 1, which is okay, integrates to a log function. 3x on x squared plus 1 degree less, so that'll integrate to a log function. We've shown that as our manipulation to get the derivative function on the function. But we've got 4 on x squared plus 3. Now we've got to keep in mind that derivative of an inverse tan function is what we're seeing there. So that's in the form of, and again, keep going back to checking your standard integrals. They would be integrating to an inverse tan function. So be very wary of that situation, that it may come back to that. It's because it's a constant on a quadratic. You see that, then it's usually going to be an inverse tan function. Again, 8 the x, irreducible factors there. Again, we do our minute transformation with these, with our fractions, and be able to get the partial fractions down and get our values for b, a, and c, so we can write our expression in that way. Again, we're going to get a log function integrates to a log function. That one's integrating to an inverse tan function, and because it's a definite integral here, we substitute our values in to get the numbers there. But the same process keeps going on. This one, we've got repeated linear factors, so our partial fractions, a on x, b on x plus 1, so an x plus 1 all squared. So we're able to manipulate to get our values and break out that fraction into 1 on x minus 1 on x plus 1 minus 1 on x plus 1 all squared, which again, that integrates to a log function, that one integrates to a log function. This one is just a normal polynomial because it's x to the power x plus 1 to the power of 2, or x plus 1 to the power of minus, if we get rid of the fraction, to the power of minus 2, add 1 to the power, divide by the power. So it's just back to that law, which is that's our very simple 2-unit integration laws. But don't forget them. It's integration. You can do any integration we like. So be very wary when we're doing all those integrations there.